Now we're going to derive one of the most commonly used fluid mechanics equations, certainly one of the most important equations in the history of fluid mechanics. It's called the Bernoulli Equation, and you may have heard of it already. I say it is certainly the most famous of the equations in fluids. And we're going to derive it starting with the energy equation in its steady state form. So this is the form we arrived at one of the earlier lectures. 0 equals q dot minus w dot. M dot in and m dot out are considered to be the same because it's steady state. So you have p over rho plus v squared over 2 plus gz in, and same thing out. This assumes that u in and u out, that is internal energy, in and out are the same. And you know for both incompressible substances and ideal gases, that is true if the flow is isothermal. So if there's no temperature change in the flow over the region which you're studying it, then you can assume that is true. If we take a simplified case where there is no heat coming in or out of the system and there is no work going in or coming out of the system, then we can simply say that these two quantities in and out are equal to each other. That is p over rho plus v squared over 2 plus gc in will equal the same thing going out. Or said another way, and this is the way that it's usually talked about, that p over rho plus v squared over 2 plus gz is actually going to be constant from inlet to outlet. And since you can kind of draw this box anywhere in a flow, that means it's constant, in the flow regime, provided it meets all these different criteria that are in the assumption of the derivation of the Bernoulli equation. So this equation right here, constant, is often called the Bernoulli constant, is used a lot because it's very simple to use. As you can see, it's a simple algebraic equation, no integrals, and it is applicable to a large number of flows. So let's take a look at some of those things. But before we get into the some of those things, let's take a look and make sure we know what assumptions are going to be made, because in truth, this equation gets overused quite a bit. It is so easy to use and so easy to remember that people tend to grab it quickly, and it is fairly, the assumptions we've made are pretty significant, some of them. So let's take a quick look at those starting in. We'll look at those again later as well, just to make sure you have them. So what assumptions have we made? Assumptions that make Bernoulli equation work? Well, the first one is steady state. That's not very restrictive. I mean, there are certainly many, many flows that are not steady state, and it's certainly important that you recognize that Bernoulli really only applies to steady state situations, but there are many, many important flows that are steady state. 2, incompressible flow. All right, so we've been doing this a lot as well. We know that incompressible flow includes, of course, the flows of liquids, which generally are incompressible substances, but it also includes the flow of gases. And we haven't really said what the condition is for gases when they are compressible or not compressible. It turns out that we'll show probably later in the class that for Mach numbers less than about 0.3, that means 0.3 times the speed of sound, gases can be treated, gas flows can be considered incompressible. So that's a simple rule of thumb for you to sort of try to commit to your memory, that if you're thinking about whether a gas flow can be treated as incompressible, gases are not really incompressible. Of course, they can be compressed. But if you have a flow with a Mach number of less than 0.3, that is less than 30% of the speed of sound in that gas, then you can treat it as incompressible, provided it's still isothermal. So as we said, we also have an assumption here that the flow is isothermal. Obviously, if the flow has large temperature changes in it, then it won't be incompressible anymore because it's going to change its volume, particularly if it's a gas, and also the derivation of the energy equation assumed isothermal. So Bernoulli is only valid if you're dealing with flows that are essentially isothermal. Finally, or not finally, we have 2 more. We have W dot equals 0. Well, that means that there's no work going in or out of the system. So generally that means there's no turbines, no propellers, in your system, that's fine. I mean, we know that there are certain flows that have those, and we just can't use Bernoulli when there's a turbine or a propeller or something else like that that is actually in the control volume that you're studying. You can use Bernoulli upstream and downstream of propellers and turbines, but what you'll find is that the Bernoulli constant will be different. And the last one is probably the thorniest one. It's Q dot equals 0. So that means that there's no heat in or out of the system. And that's going to be true when there is no friction. So this is true when there is no friction in the flow. Well, when is there no friction in the flow? There's no friction in the flow when the flow isn't moving. So basically, this means if anything's moving, there's not going to be Q actually equal to 0. So that's highly restrictive because obviously we are only studying flows that move, and the Bernoulli equation has no use for hydrostatics. It is a moving system analysis. So why, how can we ever use this? And the reality is that, of course, some flows have a small amount of friction. So, it's always an approximation. The Bernoulli equation is always neglecting all the friction in the system. If fluid is moving, it has friction. There's always going to be some friction in any moving system. So it's not going to be precise. And the question is going to be, is there too much friction for the Bernoulli equation to give us real useful engineering answers? And it's not always clear, whether that's going to be the case or not. So this is going to be the one that's the hardest for us to deal with because, it's not always clear whether there's really a significant friction. In some cases, there is friction. And if there's going to be a lot of friction, then, you can't use the Bernoulli equation. Final point I'm just going to make is that there are some books that argue that the Bernoulli equation is not an energy equation. It's based on the momentum equation. This is just an FYI. If you read textbooks, some of them will say that it's very important you understand that Bernoulli is based on a momentum derivation. That's true. You can derive the Bernoulli equation entirely from momentum arguments, but it's also true that those arguments are based on forces and movement, and that force times distance is actually energy. So I think that argument's a pretty stupid one. Yes, you can derive it based on initial momentum, basing it on the momentum equations, or you can derive at it based on energy arguments. I think the advantage of the energy argument is it really helps you to see much more clearly that this equation is really only good if you set that Q equal to 0, which means no friction.